Hello everyone. So just let me know in the chat if you are hearing me well. So we are sure that everything is fine. We will wait like a few 1 or 2 minutes, like to leave like the time for everyone to join the room. But now we can see like there are like already like 45 person. Oh, it seems that the chat is disabled. Okay. Yeah. Chat is disabled, but Q&A is working, so we can communicate with the Q&A. Okay. Yeah, so no chat tonight, just the Q&A, and we will manage with that, like even if the chat is disabled. Okay, hello everyone. So tonight I wanted to present to you like the importance of the proton and to explain to you why we are so focused on the study of the proton. And first, I will divide like this presentation in three main parts. First, I will point the limits of modern physics. And second, I will explain, based on what we are doing right now, what we just published, why the proton is the key for unification. And then you will see why understanding the proton has a great impact both in your life, but also on a societal perspective, as understanding the proton unlocks like new technologies and a better understanding of the universe as a whole. And then we will have like a 30-minute Q&A in which like you will be able to ask any question you want about what we just talked about. So let's dive in. So the three main unknown in modern physics, as we know, is the first one is about dark matter and dark energy. So as you know, as you may know, dark matter is as shown in this equation, represented by lambda, and represent the growth of the universe. And it's something that that modern physics doesn't explain. And it's just a measured quantity right now in modern physics. And the other part, so I explained dark energy, and the dark matter part is an unknown matter that we measure the effect inside the galaxy. And as for dark energy, it's not known in modern physics. The origin is not known, and the mechanism neither. The other limit in with modern physics is the unification problem between quantum mechanics, represented usually by Schrödinger equation, and general relativity. I don't know if you are seeing my mouse. Let's take the pointer so you can see what I'm pointing at. It would be easier. And the last main unknown in modern physics is the fine-tuning problem, and but more importantly, the origin and value of the fundamental constants and law of physics. Right now, they are like just assumed based on the observation, And they are picked because they are the ones that are describing the best what we observed, but they are not explained with equation or fundamental mechanics. So if we look at when physics went wrong, it begins at the beginning of the 20th century, when basically we developed the modern theories that we are using today. Like Einstein developed general relativity, explaining the dynamic of the universe. Max Planck and other Dirac also started the quantum mechanics with the quantization of the electromagnetic field. And this during this development, the main flaw were like ignoring the vacuum significance, the separation between scales. For example, one theory was developed for the atoms, like quantum mechanics, and the other theory, general relativity, was developed for cosmological studies, for the studies of galaxies, universe, etc. And they were using like completely different mathematical framework. So there was a fundamental lack in geometry. Expect in general relativity of geometry was kind of used because force were explained in terms of space-time curvature. But in quantum mechanics, for example, like geometry and mechanics was completely ignored. So we end up with a classical view, for example, predicting an energy density of the vacuum of the order of 10 minus 27 kilogram per meter cube. This prediction was just an observation. It's the one corresponding to dark energy. And on the other hand, we had like a theoretical calculation from quantum mechanics predicting a vacuum energy of 10 to the 96 kilogram per meter cube. This led to what physicists call the vacuum catastrophe, showing a huge discrepancy between the theoretical measurement, the theoretical prediction done by quantum mechanics, and the measurement done at the cosmological scale. But it's not the only time where a huge number is ignored in modern physics. Typically, this the vacuum energy density calculated based on quantum field theory is usually ignored in quantum field theory because they use a mathematical tool they call renormalization, where basically they are like subtracting this energy to get a very small physical quantities that match what the things that they are observing. So at the end, vacuum energy is just ignored most of the time. So we end up with like, as I was saying before, two completely different mathematical framework apply at each scale. And they are like very difficult to unify. There were like several attempts over the 50 last years, like string theory and loop quantum gravity. String theory, you can see like one expression over there of a typical equation used in string theory. It's highly complex, and after 50 years, there is still no testable prediction, and the theory didn't go anywhere. A good analogy to these modern theories that were developed is like comparing them to the geocentric representation. Like sometimes, especially in QED, they could like predict what we observe, but they are doing it in a very, very complex way. So, and it's very similar with what we did in the past with the geometric representation of the solar system. For example, here we have like the different trajectory, planetary trajectory for the planets in the solar system, but view from the point of view of the Earth. So it was a natural view because it's the motion we were looking at from the Earth. So when the first astronomers were looking at the planet, Mercury or Venus, they were seeing that this strange shape in the sky. And they developed over the century like pretty accurate models that were predicting the position of the planet during the year. But as you can see, like it was very complex mathematically, and everything was simplified. Oh, chat is working. Nice. Thank you. And when we changed the point of view to the heliocentric representation, when Newton discovered gravity and the way gravity was working, the representation was way more simpler and way more intuitive to compute and to understand, with the sun at the center and not the Earth at the center of the motion. And basically, it's the same for quantum mechanics and general relativity. Both frameworks are very complicated and can be greatly simplified when you change the perspective because you understand what really is happening in the physics. So basically, the big problem in modern physics is that like they remove the vacuum energy and they abandon any idea of a fundamental geometric origin explaining all the forces. Right now, they prefer to separate the gravitational force, which is the consequences of the curvature of space-time, and the electromagnetic force, which has its origin with the charge, but it's not well explained more than that. And of course, like the weak and the strong force that are only confined into the atoms in their view. So, what is key with the proton is that like it gives us a great insight on the physics of the universe. And what we built with the representation of the protons that we did is that the vacuum is fundamental to reality. And in fact, the vacuum is the source of reality and of matter and everything. There is a profound underlying geometric structure to everything that we are experiencing. And the universe has a holographic and fractal scaling property. And basically, we can see all of that just by looking at the proton. So the last paper we publish is it's called The Origin of Mass and the Nature of Gravity. And we go through all these points into showing mathematically what is the origin of the mass of the proton, which is the mass of all matter in the universe, and what is the nature of gravity. So how gravity comes from, is present at the proton scale, of course, and what is its true origin. So why the proton is important? When we trust the scaling law of the universe, you see the PSU, the Planck size, the Planck scale at the bottom, and the universe scale at the top. The proton is in the middle. And when you look at the proton in terms of the PSU, you have basically the scaling to build the other scale in the universe, meaning the scale of the stars, galaxies, and the universe as a whole. And you see a pattern, because the universe is fractal. So the patterns that you are seeing at the proton scale, at the hadronic scale, you recover it at the galactic scale and at the universe scale. The pattern is always the same. So what we published in the last paper is that the proton mass emerged from the quantum vacuum fluctuation, meaning like the vacuum fluctuation and this energy of the vacuum that was discovered first by Max Planck in the beginning of the 20th century is the source of energy that generate mass, that generates the mass of the matter, and in particular the mass of the proton. And we developed this model showing that this energy density of the vacuum generate through two screening mechanism, the black hole mass of the proton and the rest mass of the proton that is well known and well measured. And in fact, we discovered, but Nassim already published it that like a few years ago, but we discovered it again with a complementary calculation that the proton was in fact a black hole, with the tertiary radius of the proton being its reduced quantum wavelength. So yes, the proton is curving space-time and very intensively, and this curvature of space-time at the proton scale, what they called the strong force. So gravity is really strong at the proton scale, contrary to modern physics thinking and to the standard model, where they think like that gravity is very weak. We demonstrated in this paper that it's not the case. Gravity is very strong at the hadronic scale, and it's called the strong force. And everything comes more clearly when you understand that space-time acts as a fluid dynamic. So you can change the equation just to fluid dynamic equations that are way more simpler to solve than the current equations that are used for general relativity or quantum mechanics. So basically, you have a source that is the singularity inside the black hole proton, and this source is either like a water source, and the flow goes out of the proton and goes back, doing a dynamic, producing a torus-shaped dynamic flow. We will publish it in the next paper in more details, but gives you already the idea of like the quantum vacuum create a flow motion in space-time, and this is this motion that creates what we call matter. Basically, it's a vortex in space-time that is creating matter. So the proton is really important, and understanding it is like discovering the Rosetta Stone for unified physics, for physics. Because basically, at the proton scale, you have both the understanding of the quantum mechanics with the quantification of the electromagnetic field, resulting in the zero-point energy and the energy density of the vacuum. But also it gives you like a very clear understanding on how space-time curves and why the universe has holographic properties and fractal properties. The holographic properties are amazing when you look at just the proton in two senses. So the holographic principle tells you like that you can have like different definition, but both are correct and complementary. The first one is like saying that each part of the wall contains the information of the wall, meaning, and we find that with the proton, like every proton in the universe contains the information of the whole universe. That's why like when Nassim calculated like 10 years ago, he calculated the energy contained in the volume of one proton with the density energy of the vacuum. And he found that this energy inside one proton was corresponding to the energy of the mass energy of the whole universe, showing that every proton contains the information of everything. And this is very important because it gives us the clue that every proton is connected together and create what Nassim called a space memory network, with information flowing constantly from every part of the universe to refresh the information of the universe and keep a consistent view of the world. And it explains many discoveries in quantum mechanics as like quantum tunneling and intrication and this kind of strange phenomena that are not explained in quantum mechanics but just observed experimentally. So understanding the proton has a great impact on the view that we can have about ourselves and others. Like understanding that everything is connected, that you get all the information in every proton, that you can access all the information of the universe, like in any point of the universe, that you have like infinite energy basically everywhere, but it's easier to extract it from an atom than from the pure vacuum. It changed like the view that we can have of the universe and and the view that we have of ourselves, like and it ignites the scientific curiosity. It fosters a mindset of unity when you finally understand why really you are connected to all other human and more importantly to all creation. And fun fact, like it's kind of like everywhere, every time is kind of amazing to when you do like physics and modern physics with equation and a lot of mathematics, and you rediscover like ancient teaching and see, oh yeah, they were always saying that like 5,000 years ago. And it's like when we did the calculation of the proton and find the mass of the universe inside one proton, and we saw like the cover of one book of the dilemma called like the universe inside one atom, and book where he talk about ancient teaching of Tibetan culture. It's always very interesting to see like this correlation between ancient knowledge and modern physics when you finally understand like how the universe is working. So yeah, Proton connects everything. We are not isolated, and we are deeply connected with all the universe. It's highly non-local. And understanding the proton dynamic, like demystify the strange nature of quantum physics. Like if you look at the modern way to explain quantum mechanics, and in particular, like the Copenhagen interpretation, where they are telling you that one particle can be like is everywhere, and at a certain time, a particle can be anywhere, and it appears at only one precise point, only when the particle is observed. Like there are like many flaws with this kind of interpretation, and having the wrong perspective on a matter like block you from understanding further the mechanics and develop the technologies that could be developed if you had like a better point of view, a better understanding. Okay. Let's jump over that, and let's talk more about the technological advancements that are like directly connected to the understanding of the dynamic of the proton. It's what we are currently developing with Nassim and with the team at the lab. We are focusing in energy extraction from the zero-point energy, gravity control, always like from the zero-point energy, but this time like this time with the goal of curving space-time by spinning it, and the biotech part is more like with William. So I won't talk about that. It's William expertise. It will be for another day. So the key of technological advancement is to be able to reproduce what nature is naturally doing, but reproducing it at our scale. And it's not that difficult because the goal is not to be as efficient as nature, but just like being like a fraction, doing a fraction of what nature is doing at the atomic scale. We will have like a crazy amount of energy. And so like what we are doing in the lab, basically, it's understanding what nature is doing inside the proton, and scale it at our scale, like at the laboratory scale, to have something that we can operate with the current device we have. And from our understanding of the proton, one way to model it like very simply, but in a very efficient way, is to use, for example, the electronic analogy of the harmonic oscillator. For example, in this example, you have like three LCR oscillator with capacitor, inductance, and resistance. And in our model, we showed that the resistance act as the mass, the dissipative energy, radiating energy that is curving spacetime, and it's represented by the mass. And the capacitance and the inductance act to represent the oscillation of the flow inside the proton. So you can see like the torus flow that will act. And the energy is transferred between phase by a phenomenon similar to inductive coupling. And the charge at the end, the charge is particular, the electron is really particular. When we mean in this presentation, charge mean the electron. But the electron is particular. It doesn't really radiate mass. It's a different case. And when you understand that, you find like a very interesting equilibrium between the flow of energy, in this case between the potential energy and the momentum energy. And you naturally find the golden ratio. And as you may know, like the golden ratio is really key at every scale to understand how the flow organized. And naturally matter like organized matter, living things, organized following the same flow, the same pattern. That's why you can find the golden ratio at every scale, so at the galactic scale, at the planetary scale, and at the skin level scale, in the plants, everywhere. Because everything tries to be optimized, and the best optimization is to follow the natural flow of things. Of course, like we can build inefficient technologies that most of the technology we are using, but it's inefficient in the sense that we are consuming a lot of energy running this kind of device. And a device using the right proportion doesn't consume energy. Actually, it produces energy because it goes with the flow. And going with the flow, basically, it's not like amplifying it, because the flow is very intense at the Planck scale. It's just like taking a fraction of it and extracting it, meaning like scaling it through the scale up to your scale where you can use it. A nice analogy would be like a windmill. The windmill will rotate with the wind, and of course you are not like extracting all the kinetic energy of the wind. You are just taking a fraction of it, but you are scaling the motion, like meaning you are taking the kinetic energy of air particles, so very teeny particles, and you are transferring it to a large system where you can mechanically use this energy to produce electricity or mechanical force. And it's the same that Nassim built with the resonator. So it's the key technology that we are developing here in the lab, both for extracting energy from the zero-point energy and to produce gravitational effect. Because the end goal is gravity control. It's not just producing electricity. The electricity production is just the natural first step toward gravity control. So basically, the resonator is a reproduction of what the proton is doing. You have like the core with the singularity, and the plasma flow circulating around it, and the magnetic field conditioning the plasma flow. So you have a nice double torus. And so the idea is to, like the windmill, to organize first to organize the Planck flow, so it's current and with a collective motion, and using this flow to move the plasma, and then when you have like a nice plasma moving, spiraling around, you can extract energy, and you can curve space-time, because space-time curves when you have like a toroidal flow, a vortex flow, of a plasma, for example. Other consequences of all this discovery around the proton is, of course, like it would change the way we are teaching physics and the way we are teaching everything, because seeing the proton shows you that it's key to not look at only on one part of the question, but take every question as a whole. Like the proton seems like very little, having a little mass, but understanding that that gravity must play a big role in proton, because gravity plays a big role in the universe, was the key to understand that proton was in fact a black hole, and was very full of energy. So yeah, more philosophical stuff. Let's jump to the question. I will look at some of the question and select a first. Let's see. So I will look at the question, bring you up to the video. If you want to talk, ask your question directly. Let's start with the first one. Jamie is asking, do you think zero-point energy, when discovered, will unveil the unified field? Jamie. You can talk.
Yeah, I'm just wondering if we're discovering what holds the universe together. It sounds like that's what you're saying.
Can you repeat? I missed one the beginning. Yeah, Jamie.
Hey, bud.
Yeah. I'm hearing you. Yeah.
I'm just wondering, it seems like you're saying the proton could be the link to the unified field where we begin to understand the entire fractal or holism itself.
Yeah, exactly. It's the point. It's like I wanted to do this quick presentation because you may ask, like, why are we studying that much the proton, and why the mass of the proton, or why the radius of the proton matter? Why is it that important? And as you said, like studying the proton is key to understand that the zero-point energy is the source of matter, is the source of the mass of the proton, is the source of the dynamics that we are seeing at the proton scale, with the strong force and the weak force. So it was really essential to understand that, and understand that basically the proton was using this zero-point energy to exist. So matter is built on the zero-point energy. That's why, like, you can extract a zero-point energy using matter, using the same dynamic as matter is doing.
What are the effects of the observer effect in consciousness relative to what you're seeing and understanding?
The observer, you need, to answer this question, we need to define what we are calling the observer. I assume that you are not calling the observer what in the same way they are calling it in the Copenhagen interpretation in quantum mechanics. Because in quantum mechanics, the observer is not defined. In your case, you mean like how one person can interact with this field, you mean? With how consciousness interact with the zero-point energy?
Yeah, I mean, I'm getting at the heart of like why things change when there's an observer, when we measure things. That aspect of physics.
Okay, so you are talking about the Copenhagen interpretation.
Yeah.
Yeah, this part is wrong. I mean, is wrong in the sense that they can't define an observer. They can't say that if an observer needs to be a human, of course not, because if there is no human, the universe keep like spinning, keep happening. So it's not a human. Is it like a fly? Is it a molecule? Is it? It's not defined. So
and yet it changes things when we know that it changes when we observe. So that, you know, how can you exclude the change?
The right explanation, for example, for the double slit, it's more like just to remember to everyone what is the double slit experiment, because usually it's where you are seeing like the change of the observer. It's like when you have like a particle wave duality, you send a particle through two slits, and you see patterns. I'm missing the English word. you see those patterns, and when you observe, you lose the patterns. And our way to explaining it is like first, a particle is a particle and a wave at the same time. So when the particle moves, it creates a waves. But when you add an observer, meaning like in this experiment, you add a device to measure if the waves, if the particle goes through one slit or the other. When you put this device doing the measurement, it perturbs the waves. The waves lost, like is slightly modified, and so you lose the interference pattern, because the interference pattern is very sensitive to the phase of the wave. So as soon as like you lose a little bit of coherency, you lose the pattern. It's a classical explanation for photon for light, for example.
All right, thank you.
Thank you. So let's take another question. Thank you, Jamie. So we have a question from Carla Geldamez. Yeah, you can talk, Carla. Yeah, not hearing anything. No, Carla, I can't. I can't hear you. Like, I don't know why. No sound.
Can you hear me now?
Oh yeah, now it's working.
Okay, that's interesting. So somehow this other speaker is not working. Yeah, no, I just, good morning. How are you doing?
Good, thank you.
Good. It's nice to hear you guys. I guess that the question regarding the observer and the double slit experiment, I mean, as you know, there are many different interpretations, and there's also different interpretations in relationship to the idea, I suppose, Einstein's perspective, you know, if a human isn't there, is the moon gone? But I think that those sort of perspectives have a very limited concept of what consciousness is. So they generally think about consciousness as a localized human conscious being, and versus, in a way, there's an aspect in which one thinks about non-local, expansive consciousness or mind at large, through which Einstein's say, you know, in a way, rejection of the even of entanglement and of the idea of the observer's primary purpose in the evolution, in the creation of the universe, has been mistaken as being human-centric, because the perspective has been thought of the human as the localized being. But I think that there's a sense of, from a mind, a large perspective, the universe evolutions as well as the universe formation are all intrinsic within the primary existence of consciousness. And so that is not matter that is primary, but that is consciousness that is primary. And I think that Penrose would in many ways agree. And we would go back into Gödel's theorem as a possible avenue of being able to debate this within the perspective that there exists solutions and farther questions to a problem than within a hypothetical say set of axioms. And then when it comes to the double slit experiment and the CCD detector as being the observer, quote unquote, I mean, there are anomalies on that too, right? So from von Neumann's perspective, which would probably be, I would say, one of the most respected ones, because at the end of the day, he was the originator of the mathematical foundations of quantum mechanics through operator theory, that you would have a von Neumann chain, which was his invention, that even if the CCD is there, the CCD is at the end of the day linked to a human observation. And whether the human is within the room or outside of the room, that the existence of consciousness is a factor that you just cannot simply take out of the equation, is the inherent part of the equation. And that equations, mathematics, and Platonic forms, as going back to Penrose, originate from mind consciousness.
Yeah. Thank you for sharing that. I think, yeah, it's a nice topic that will be discussed more in detail by William and Nassim, and they will go to in July to Barcelona to the Consciousness Conference, and they will have the opportunity to discuss this topic with Penrose and others, and I think it will be live streamed, so it will be a great occasion if you are interested in this particular topic of consciousness and how consciousness relates to our works and to physics. You will have like many answers if you have the questions. Yeah. Thank you, Carla.
Yeah, sure. Yeah, you're welcome. It's an observation that I wanted to make because I think that this is a discussion, not just a question and answer. And as a physicist and as a training a scientist, I think that it's okay for me to make this observation. I know some things a little bit differently, but I think that it'll be great to, see a debate on von Neumann's chain, as well as Penrose, Gödel's theorem in the perception of consciousness as being primary.
Yeah, thank you.
Thank you.
There are like so many questions. We won't be able to answer to everything. Is there a way to vote to the question, so you could vote to the question you want an answer in priority? I have this one. Simon is asking a question about the proton. Let's see if Simon can join us. Simon.
Yes, hi, can you hear me?
Yeah.
Yeah, okay. Yeah, I was curious of if I understand it correctly, why does the neutron decay into a proton quickly? And
yeah, this is another point, good point, that the proton, contrary of what say the standard model, the proton is really a particle and a fundamental particle. And the best example, the best proof of that is like every other like particle element decays into a proton. And for example, the neutron decay very rapidly into a proton, and it forms like a proton and an electron. But most importantly, when you look at the CERN experiment with the accelerators, like they are creating quarks and gluon quarks and various mixture of a lot of particles that they found in their standard model. But at the end of the experiment, what really remains, oh, we lose light. It's just protons. So at the end of the experiment, when you look at the final product, it's just proton, electrons, and photons. So basically, you smash protons, you create like a bigger particle, a bigger quark that have more energy than a proton, and at the end, like they cool down and they make protons again, showing that the protons are really the key. I'm coming back, just putting the light on.
Okay.
Sorry. You have a second part to your question?
Yeah, is the neutron the one that decays first and naturally when it's separated? Is it spinning slower? Is that why? Conservation, or is it like, is there a certain yeah, I guess that's the second question or part, like, is the neutron one of the first ones to decay naturally into a proton when it's separated, if I understand that correctly?
So when you look at the nucleus of an atom, it's always, apart from the hydrogen atom, which is only one proton, you always have like a mixture of proton and neutron. And it's not explained, but usually you have this rule that you have twice the number of neutrons than proton. And when you have like a fission, like meaning like you are splitting the nucleus of an atom, and you are like basically you are emitting neutrons. When a neutron exits the nucleus of an atom, it's rapidly decay. I think it's in terms of microsecond. It rapidly decay into one proton and one electron. And of course, like there is the conservation of energy and the conservation of angular momentum, but the standard model doesn't give you any information about the structure of the nucleus of an atom and the dynamics between proton and neutron and this kind of stuff. So just know that some nuclei are stable, some other are not stable, and we call them like radioactive nuclei, radioactive isotopes. And usually radioactive isotopes are bigger than the stable isotope. It's not always the case.
Okay, thank you. That was very clear. Thank you. Yes.
We have time for one or two other questions. There is a question of Zach about gravity. Who's been testing? Zach.
Okay. Can you hear me?
Yes.
So, Newton, I'm not a mathematician, but Newton's formula for gravity, is based on the weight, the mass of whatever it is. So if gravity is strong at the proton scale, does that mean Newton's formula for gravity is wrong?
No. So, as you said, like Newton is proportional. The force is proportional to the mass. That was That's the formula Newton found. And it's working perfectly well at the scale of the solar system, for example, and at the human scale when you calculate the gravitational acceleration on Earth. But it's just an approximation, and that's what Einstein demonstrated when he developed general relativity. He demonstrated that Newton was an approximation at low gravity, at weak field. It was a good approximation to gravity, the Newton law. And what we developed when in the last paper is that we showed that using Einstein field equation, where we put as a source term the 0-point energy, you can actually calculate the real gravitational acceleration at the proton scale. And what you find is that the gravitational acceleration near the really center of the proton is equivalent to the strong force. And then later on, with the decoherence of the 0-point energy, the decoherence of the field, the acceleration weaker, and we recover the Newton law, so in more far away.
Does this mean that
So
the
long distance.
gravity is really just an aspect of the strong force, or vice versa?
Yeah, it's more like the strong force, like they name it just by after measuring it, they name it strong force because it was like stronger than the electromagnetic field. And they didn't have any idea about quantum gravity, so they assume that, oh, it's a new force, and they name it like strong force. The weak force, they already unified it with the electromagnetism, so they already know that it's basically it's electromagnetism.
So really, my question is, does this change the four basic forces of the universe, that the strong force really isn't?
Oh, yeah. Basically, it's what we showed in the last paper. Basically, it's just general relativity. With general relativity, when you add the source term from quantum mechanics, like the 0-point energy, you recover all the dynamic of the proton. So you recover the strong force.
Thank you.
And the residual strong force and everything. So basically, yes, you unified all the four forces in one.
Thank you so much.
In one mechanism. Yeah, you're welcome. So let's take another question. So there is Hugo C that has a question about the plasma interaction with the quantum flow. Hugo, you're online.
Okay, can you hear me?
Yes.
Yes. Salut Olivier.
Salut.
So yeah, I was thinking about how do you couple the plasma dynamic with the quantum vacuum? How do you interact? Because I was questioning, I was thinking about how do you interact with it?
Yeah, so the tricky part is like we are just we want to act at very different scale. You have like the motion of the Planck plasma flow, 0-point energy, that is at a very teeny scale, and usually, like you can see in the vacuum, you can't feel it. You can feel it in matter. It's very dense, and it's still the same thing. It's the Planck plasma flow, and so the tricky part is to be able to create a collective motion, because matter is that it's a collective motion of the Planck plasma. So you want to artificially create a collective motion and then extract a teeny part of energy of this collective motion. And one key understanding to create this collective motion is a good example is the pendulum. When you look at there are like a nice video of a pendulum and how to couple pendulum. And you can see like actually it's with metronome usually they're doing the experiment. You can find video on the internet. When you just weakly couple metronome, you can see that they will naturally
create coherence.
Create coherence, and at the end, like a very short time, you will have this collective motion. So basically, what you need to do in the laboratory is to create this tiny coupling, this little coherence, and then like everything will start moving naturally in a collective manner. And when you get that, like you will go through scale. You will naturally go through scale, and the goal is to achieve like the laboratory scale you are building your device, and then like you can start extracting energy from this collective motion. That's why we are using plasma and this kind of stuff, because it couples. The coupling usually it's easier to do it like electromagnetically. And it's the way the electron is working, so probably it's the it's the best way to go.
There's a link, yeah.
Yeah, it's a little hint. Just look at nature and try to reproduce it.
Yeah, and you will understand everything better. Yeah. Okay.
Go with the flow.
And I was thinking maybe, is dark matter a produce of the vacuum field that is not expressing itself fully?
Yeah. So dark matter, I don't know if I was very clear in my first slide, but dark matter, just to remember to everyone, it's what they add to galaxies. It's matter that they can't observe, but they are seeking. We need it because we are seeing a certain dynamic in galaxies where stars, based on their model, should go at a lower speed than the speed they observed they are going. And I think the best explanation right now, we didn't develop fully the equation, but the best explanation is what Nassim is always saying, is like they are forgetting the flow of the space-time flow, the flow of the vacuum. It's like if you were trying to understand the dynamic of the milk in the coffee. When you are spinning the coffee and you are adding a little bit of milk, the milk will be the stars in the galaxy, and you are trying to understand the dynamic of the stars without considering the coffee. Like you are missing the fluid that is dragging around the milk, the fluid that is dragging around the stars. So that's why like dark matter represents, I think it's about 60% of the mass of the galaxies, and it's just that they are ignoring the flow, because one key part that they remove from the beginning at the beginning of the modern physics is the ether. So they remove the flow, which is crazy because it was the base of the reasoning of Maxwell when he developed the first like big theory, the electromagnetic theory. But they removed the flow, so it was harder for everyone to build a consistent theory upon that. And it's crazy because general relativity is basically the equation are like a flow dynamic equation, just flow dynamic equation, but without a flow, without a fluid.
That's original.
Yeah, it's just space-time, a mathematical construct. But at the end of the day, it's like I was explaining for the split experiment. The double slit experiment is not a particle or a wave. It's a particle in a flow producing a wave while it's moving.
Yeah, like the droplet experiment with the silicon bath. I don't know if you.
Yeah. Like the droplet on the silicon bath, and you can reproduce all the mechanical, the quantum mechanical strange effect with a mechanical experiment.
Yeah,
it's a
with
very
the
good
fluid, with
Yeah.
different pressures.
Yeah, in
Okay.
fluid dynamics. Yeah,
Okay. Yeah.
it's a very
So
good analogy.
so that was the surrounding fluid that
Yeah.
that explains it all.
Yeah,
Okay.
I'm looking at the commentary in the chat. Yeah, the Michelson-Morley experiment. The funny thing is, like, they were trying, Michelson and Morley, they were trying to prove the existence of the ether. They failed because, like, the setup wasn't enough precise to prove the existence. But of course, they didn't disprove the existence. They just proved that that their experiment wasn't precise enough. And after, like, they measured the ether, but they called it prime dragging. But the dragging was just done by a mathematical object, space-time. But to
Without
measure
explaining
it,
what
like,
was the
many
frame.
times. So basically, yeah, it's not really clear why they remove it, like why they remove 0-point energy everywhere, if like if it's purely scientific or also politic. But like they are, yeah, it's confused.
Yeah, not clearly defined. Okay.
Let's take.
Thank you.
Thank you, Hugo.
Yeah, thank you, Olivier. See you.
See you. Let's take a last question. And I recommend you to keep your question, and there will be like talks, and the next one will be Cyprien. So I'm sure he will be happy to answer to all the questions I couldn't answer tonight. Let's take the last one from Axel. Axel, you're on.
Bonjour Olivier, do you hear me?
Yeah, I can hear you.
Nice to see you, Olivier. Last time we met was in Monaco, if I remember correctly.
Oh,
And,
yeah.
I'm really happy to see you today. Thanks for all the great work you do with the team and of course with Nassim. Following you for a long time, Olivier, I'm wondering, where are we from the Big Bang in terms of technology production, in terms of making it real? And behind the question, I guess, are my two secondary questions, which is the theoretical framework you're working on the right one to create the technology you're looking for? And the limitation is in the technology, the physics of it, the physicality of it? Or do you still discover things as you move along and you still need to work on the theory in order to give birth to anti-gravitation and free energy?
Yeah, it's a good question. The answer is not quite simple. It's more like we have enough theoretical background now to understand what we are doing with the application, with the hardware. We didn't solve everything. we need still to develop more the theory and to be more accurate, but we have the ground now, the ground base to understand what we are measuring and what we are creating in the laboratory, which is good, like, because the roadmap is more clear. The technological roadmap is clear now. So we have a good pathway to have like first application, small scale application, larger scale, like we need more work, even on the theory. But yeah, we have a really good roadmap to a nice breakthrough, and I hope we will be able to communicate more in detail soon about that. But you know, like communication strategy, what we can tell and what we can't tell.
Yeah, fully understand that. And overall, Olivier, do you see a traction of your framework now in the mainstream academia, or is there still resistance? Because what you said about the point of view, simplifying things like the heliocentric system, for me resonates. I'm not scientific in the sense that I can understand the equation, but all what you're saying, the fact that you find phi and you find a relationship and that everything is fractal and can be explained, simplifies everything. So do you see traction in the mainstream academia to follow you, or where do we start?
We start seeing like more people interested in what we are doing. It's still like a small number. We were hoping to a more a bigger motion, but you have a huge inertia in the scientific community, and the time frame in the university are not the same. They are like way slower. Like for them, like 1 year, 3 years, it's like it's nothing. For us, it's it's a huge change. So yeah, so for us, like it's slow. It's the reaction of the scientific community is slow, but at one point they will follow. We will keep like publishing, and I think like there will be a wake up call when we will show the device. Because they don't have any other physical framework to explain what we are doing. So they will have to accept that they need they already know that they need another framework, because the standard model is limited, and they can't find any good answer to dark energy and dark matter. So in both at the cosmological scale and at the quantum scale, they have like big issue, and they know about it. They know that their attempts had failed, both with string theory and with quantum loop gravity, or this kind of theory that didn't produce any technological application. In our case, we explain what we are seeing in the laboratory, like the standard measurement, but we also explain like phenomena that couldn't be explained with the standard point of view. So I think like especially with the last paper that we will publish, they are having everything from general relativity. It's very strong mathematically. So small step after small step, they will start understanding. Yeah,
it's coming. Thank you, Olivier. Keep up the great work. Thank you.
Thank you. Thank you, everyone. So it was a pleasure discussing with you. First attempt for me from a long time. I think I need more training. And I really enjoyed your question, and I'm hoping to see you next time. Have a good evening, everyone. See you soon.